Last year, we started to bring to our group something new, that is triboelectricity, as a novel tool for the development of our devices. But first, what is triboelectric effect? I think everybody knows. The triboelectric effect is the ability that some materials has to accumulate charge when we rub them, right? So when we take a balloon and scratch in your hair, and the balloon starts to attract your hair, that is electrostatic charge that accumulate in the balloon and in your hair, right? That's triboelectricity. And this phenomenon is known for centuries, but until today, a lot of groups are trying to understand the main concept of how this works, how the charge accumulate. It's just electrons, it's electron and materia, and it's both. And that's a lot of controversial research about that. But still, a lot of groups are using triboelectricity for a lot of different applications. For example, this one is for water disinfection in nanoladders, published in nanoladders, using copper oxide nanowire. And that another use electrochemistry isolators. That's really nice, published in Nature. And this another one is in energy area. It's about the triboelectric generators. So that's a lot of areas that we can use triboelectricity. And we were thinking, what else can we do with triboelectricity? So in our group, what we do, working with paper-based device, what can we do with triboelectricity? So one of the problems that we had with paper-based device was the sealing part. So we tried a lot of things. The first thing that we tried, we published in 2014, was using a device like this with 2 pieces of PMMA. It's really an interesting approach. And with this approach, we saw the importance of sealing or of using a closed device with paper as platform. So that was the first time. And we were thinking, what can we do to be more simple, more easy to use, and every laboratory can work with? So we started to think a lot of things that we can do with sealing methods, using glue, with 2 pieces of PET, and putting glue on the paper, and Scotch tape, or lamination. And everything that we tried was not reversible, so we had to if it's not working, we have to put it away. We couldn't open and put some reagent inside the device, so that was a problem. Why not use chard? We thought. The chard, the advantage, it's simple, has low cost, easy to use, it's non-destructive, it's reversible, and it's fast. So we tried something like this. We have a paper and we have a PET. And looking here to the triboelectric series, when we have up here the materials that has the ability to become more positively charged, and down here the materials that has the ability to become more negatively charged. So the paper is here in the up part, and the PET polyester is here, negative part. So when we rub them, the paper will become positively charged and PET negatively charged, right? And they can attract each other. In this way, we can seal the paper, putting the PET in both sides of the paper. Right? Here's the first, it's not a beautiful movie like the movie that Professor Albert was showing before, but it was a first test that we did, just scratching paper and PET, and we saw that the PET really attract the paper, and it was reversible. It's something really important. And we could do that all day, so this was really nice. So with this in mind, with the motivation of this study, we published in Laboratory last year a paper called Triboelectric Effect as a New Strategy for Sealing and also Controlling the Flow in Paper-Based Device. That second part here, the part of controlling the flow, I will talk about that in the end of this presentation. The construction of the device for this study was really simple. We took a Wattman paper, a chromatographic paper, and using a wax printer, we print a channel, right, with 80 millimeters long here, straight channel, with some lines on the sides just to measure the distance that the liquid flows through the channel. And for the PET sheets, we cut it with a silhouette plotter, but we could cut with scissor also. And the procedure to fabricate that device, that closed device by triboelectric effect, was simple also. First, we use two pieces of PET and scratch in two different materials. We rub PET in Teflon, that is more negative in the triboelectric series, so the PET will become positively charged. And we rub the second piece of PET in PMMA, that is more positive, so the PET will become negatively charged. So we can have both charges on PET on the same material by rubbing different in the other materials. So we have a positively charged PET and negatively charged PET. So we didn't have to scratch the paper. So we didn't have to scratch the channel. And here is the analysis. We did the analysis measuring the flow rate. So the difference of the flow rate for the open and the tribosealed devices was really different. When we have an open device, the liquid flows until 40 millimeters and then stops because of the evaporation, right? That is some problem when you use paper-based device. But when you have a closed device with the triboelectric way, tribosealic that we call, so the liquid flows until the end, reach the end of the paper in just 10 minutes. That was really interesting to see. And we were talking, if the charge had something to do with, we didn't know. So looking here to the Lucas-Washburn equation that detects the liquid flow in a capillary surface. So the distance that the liquid flows through the channel must have linear relationship with the square root of time, right? So here we have almost linear relationship when we have the tribosealed, but when we have the open device, of course, it's not linear. And if it's linear here, so the charge has nothing to do with it, with the flow rate. It's just the liquid flowing in a capillary surface. So, and to confirm that, we try to do another experiment. At this time, using PET, closing in both sides, but without charge. Right? We put some glass slides to keep the PET flat in both sides of the channel. So we did the same experiments, and as you can see, for the uncharged and tribosealed device, we have the same behavior. So the charge has nothing to do with it. The charge was used just to seal the PET. So we did also another experiment, changing the humidity. As you can see, for the tribosealed device, the humidity doesn't change a lot. It's almost the same. In 10 minutes, the liquid reached the end of the device. But to the open one, as you see, if you change the humidity, you change the flow rate. So it's important to see when you use paper-based device, right? Especially when you want to use microfluidics. So, but looking here to this experiment that we did after, the charged surface can attract water. So how this works? Why the charge didn't do nothing to the flow rate in a paper? The main idea for us is because when the liquid goes in contact with the surface, the charged surface, the liquid discharges it. And discharges it only in the position where the liquid is in contact with the PET. So in the other part, it's still charged, so the device is still sealed. And how can we use this charge? But this time to attract the water and delay the flow. Maybe we can delay the flow with that. So we put some spacers to put the charge away from the channel, right? To not have contact, liquid have contact with the charged surface. So with that spacer, we could see that for the uncharged here in the charger, we have a delay. So for the charged surface with this spacer, we delayed the flow. So by using these spacers, we can delay the flow. We can control some. Maybe we can control. And we did another experiment to see if we can control. And this one changing a little bit. It's a simple experiment. We changed a little bit the design of the channel. We put some 2 entrances for the liquid, and see the liquid reaching each other right in the middle, right? But when we put a hole right here in one side, so this part in red here is open to the charged surface, right? And here a bigger hole, so we can shift the meeting point of the liquids to the left because of the presence of charge here in that part. So when we increase the area that is in contact with the charged surface, we can shift even more. So we can control the flow rate in one of the channels by increasing the area that is in contact with the charge. So regarding this paper, we can talk about we could seal and control the flow in paper-based device by using triboelectricity. That was the first time that someone tried to do that in paper-based devices, and we did another tests. This time using another type of device, using with inkjet printed. We inkjet printed some electrochemical cell right here in one polyimide part, and the PET part up here, and just a piece of paper in the middle. And we did a flow experiment, and as you can see, this is actually the real experiment. We could do the liquid flows through the channel until reach the electrochemical cell. So with the open device, the liquid just reached until here, didn't hit the electrochemical cell. So that's really important to see this working. So what else we can do with triboelectricity? In our laboratory, we try to create microfluidic channels also by using some PET masks, and we charge the PET masks, and we put in contact with the paper, and then we spray some hydrophobic ink, and create the pattern. And that's actually a picture of the device that we fabricated with this strategy. And we can also create 3D devices by using pieces of charged PET instead of double-sided tape. So you can, it's reversible. It's not. We don't need to put away the device, and we can also maybe separate charged analyte. That's something that we are trying right now. So that's a lot of possibilities of using triboelectricity in our area. And in the end, now I would like to thank the UNICAMP, Institute of Chemistry, INCT, the founding agents, and I would like to thank also the organization of a workshop of microfluidics for the invitation, for the kind invitation, and also my group. And thank you for your attention.
Okay. Questions?
Nice presentation. 2 short questions. How long does it take? How long can you keep it? And about the hydrophobic ink, is it commercial or homemade?
The first one, how long it takes to... Can I keep it? We tried the experiment, a little fast experiment. We could, this takes like 22 days attached to the paper, the PET attached to the paper without any change. So we didn't try more than that. But we have to do, and it's reversible, so you can put it away and put it back. Only if you watch then is discharged. And the second one is the hydrophobic ink. It's a commercial one. It's for painting.
Have you ever tried to use polyelectrolytes to cover the channels?
Have you ever tried what?
Polyelectrolytes.
Polyelectrolytes?
Yeah.
No, I didn't try, but we are trying right now to see that if it has some influence on that. And also in biological elements. So if have some influence on biological molecules.
Yeah.
So we are trying this right now.
Okay, thank you.
More questions?
Yeah, thanks for a very nice talk. How well can you control the charging? You say you rub it against Teflon or against something else. Is it saturating and measure? Do you measure the charge at the surface?
We try to measure once, but we use the strategy that the Bard use in Nature paper. It's about electrochemistry isolators. The same strategy. We rub them until we hear a sound of electricity going from one surface to another. It's like you reach the maximum charges in
you get
the
discharging or something.
Yeah.
Is there a way to measure it? How much charge? Electrometer or so?
We tried to measure once with a multimeter and putting some
very close.
Some electrodes, and we rub, and then we put the electrode and see the peak of potential that we had there. Yeah. So we tried to measure that once. Was not actually a measure. It was with a multimeter, but we tried once. It was really high, the voltage.
Okay.
Any more questions? Okay, so let's think again, Everson. Antes de passar para a próxima apresentação, tem alguns avisos aqui do professor Fracasso me passou, né? Todos os dias vocês devem assinar a lista que vai estar lá na secretaria, né? Tá? Pela manhã, então, sempre assinar a lista, todos os dias. Pela manhã, há um café, né, bem simples aí na chegada para vocês tomarem. E, com relação aos certificados, eles serão impressos e entregues na sexta-feira. Tá? Após o fim? O término? Ou... Bem, a nossa terceira apresentação será realizada pela professora doutora Carolina Palma Navieira Cotta. A doutora Carolina concluiu sua graduação em Engenharia Mecânica em 2004, né? Universidade Federal do Rio de Janeiro, onde também realizou mestrado, doutorado, pós-doutorado. Atualmente é professora adjunta, do programa de Engenharia Mecânica e do programa de Engenharia de Nanotecnologia, da COPPE, UFRJ. Desde 2011 é bolsista Produtividade CNPq, nível 2. Né? Tem experiência em fenômenos de transportes, em micro e nanoescalas, né? Atuando em microfluídica, métodos inversos, híbridos, termografia por infravermelho, intensificação térmica com nanofluidos, e nanocompósitos e microsistemas térmicos. Bem, vamos só colocar aqui a apresentação. Então, em nome da comissão organizadora, né, eu gostaria, então, de agradecer por aceitar o convite para fazer essa apresentação. Tá? Então, passo a você a palavra.
Obrigada, Dozil, pela introdução. Obrigada, Fracasso, pelo convite. Today I will, let me try to use this. Okay. So, as Professor Dozil mentioned, I'm a professor at the Mechanical Engineering program and Engineering of Nanotechnology program. So I come my background is in engineering thermal science, and especially since 2011, I have been moving to heat and mass transfer to microsystems, and today I will briefly present, giving an overview of what we do in our lab at Rio de Janeiro, and talk a little bit about formulation, mathematical model, physical models, and using these forward and inverse analysis and non-intrusive measurements applied to microfluidics and microsystems. So we work in this lab MEMS. It's the Nano and Microfluids and Microsystems Lab. It's a new lab since 2011. So we have now 29 collaborators, 2 professors, 4 postdocs, 9 PhD students, 6 master students, and 7 undergraduate students. And what we do there is our main area is heat and mass transfer in fluid flow in micro and nano scale. So we work with complex fluid, and I will briefly show some of our application areas, but all what they have in common is working in heat and mass transfer. So one thing that I think it's a good thing in terms of our expertise is we are able to deal with the microsystem fabrication. We don't have a clean room. We have a dirty room, but we work with this some low-cost microfabrication platforms. We do some experimental analysis using as much as possible non-intrusive measurements. We do computational analysis using this forward analysis and the inverse analysis. Just to be sure that everyone knows what I mean in terms of forward analysis and inverse analysis. What we call forward analysis is when you know everything. You know the physical properties, you know the source terms, you know the initial and boundary conditioning, geometry, everything. And then you are able to calculate the desired potential, the temperature field, the velocity field, the concentration, everything that you want. But usually the real world is not forward problem, it's an inverse problem. So what we call inverse analysis, you measure something, you measure the potential, or you measure the velocity field, or you measure the concentration field, and then you make some estimations. You estimate the thermophysical properties or the source terms or the geometry, and then you are able to identify things that usually are unknown in your experiments, in your real conditions. So in terms of simulation approach, what we do in terms of the forward problem, we use this integral transform technique. It's a hybrid method, and some collaborators, our collaborators, use these fine elements using the console multiphysics platform. But me and my group, we build our own code using these hybrid methods, this integral transform technique. And in terms of the inverse analysis, we use this Bayesian inference, since instead of estimate a deterministic property or deterministic initial or boundary condition, we estimate a posterior probability. So we have as an output of our inverse analysis a posterior probability from where we can have the mean and the deviation, the interval of confidence. And in terms of experimental and measurements capability, as I mentioned, we use this non-intrusive, we try to use this non-intrusive measurement, so we use a lot the infrared thermography, even when we don't have, our application is not essentially in thermal science. We use hot water or temperature as a tracer to be able to use this platform, non-intrusive platform. So we measure the temperature at the external surface of our microsystem, of our substrate, and we are able to make inference what is happening inside the microsystems using this a mathematical model that couple what happened in the solid and in the liquid and in the whole structure. And also we have some some experiments in using particle image velocimetry and laser-induced fluorescence to measure the velocity field and the temperature field inside the microsystems. So those platforms are non-intrusive measurements, and we use as much as possible in our experiments. But when we started in 2011, by that time we didn't know what kind of application we will face. And thinking on that, it was not clear what kind of microfabrication platform we will need. So we decided to invest and have some platforms, different platforms, to be able to work with different substrate and then be able to work in different areas and collaborate with different groups. So we had the opportunity to have Professor Luiz Otávio Saraiva Ferreira from UNICAMP and advised us in which platform we could start. So we started with the photolithography, a low-cost photolithography that make us able to work with polymer, and here you can have an idea about the minimum dimensions for each platform. Then we have two laser ablation systems